let us begin with our first speaker, Ms. Wafae, who's going to present her work entitled Integration Human AI Collaboration for Automated Product Backlog Generation in Agile Development. So, Ms. Wafae, you have exactly 12 minutes. 12 to 15, no, we can take 15. Okay, so you have, you can start. Thank you.
So good morning, everyone. Thank you for being here. Today I will present my research titled Integrating Human AI Collaboration for Automated Product Backlog Generation in Agile Developments. And this work introduces our system, Auto Jira Backlog. So our objective is to explore how artificial intelligence combined with human expertise can support one of the most critical phases in Agile process, which is the creation of product backlog. So as you know, the creation of a product backlog is recently a manual process which is time-consuming and depends subjective interpretations with human dependence, and that leads to a negative impact into the process, especially in a phase of consistency and low traceability and reduced agility. So as you know, in recent years, artificial intelligence was included in Agile processes, but the prior works have explored AI in Agile, especially in task automation, user story generation, and decision support systems. However, most of these works focus on a partial automation. Donc we don't have an end-to-end automation of these systems. Few consider multi-steps reasoning pipelines, and almost of those works known integrate a human in the loop systematically. So all that leads to a special research gap, which is how to fully automate a backlog generation while preserving human-centered design. So how to combine these two processes, AI, artificial intelligence, and human expertise in the phase of creation, the product backlog, and especially Jira product backlog. So based on this gap, we defined three research questions. The first one, can fully generate a backlog from user insights. The second is the system domain independence, and how do humans perceive this collaboration. So our contribution in this case was the creation of our system Auto Jira Backlog, which is a multi-agent system composed with two agents. The first one, the research agent, is responsible for vision analysis, for dialogue with the user, requirements generation, and the personas generation. The second agent is responsible for requirements analysis and Jira backlog generation. So the input of this system is the product vision, composed with the name of the product, the vision, which is the target audience, the current situation, which means the present state before using the product, and the desired situation, which is the improved or ideal state after using the product. So the first agent is in contact with the stakeholder, with the human in loop, and the outputs of the first one are the requirements and personas. The second one, the output is a Jira backlog, product backlog, which is a CSV file that can uploaded in a Jira platform. So this framework is realized with three technologies or three framework. The framework QAI and the LLM Llama 3 and Grok for have some fast execution. So here we will respond the why questions that we have. So why not a single model? And we are choosing to work with a multi-agent model. So because a single model is a monolithic reasoning, we don't have a rule specifications in single models, and it's so hard to ensure traceability. Why agents? So because we have a role specifications, we have a step-by-step, as you know, reasoning, we have a better interpretability. Why QAI? Because it gives us a role assignments, a model design, and simple orchestration. Why Llama 3? Because it's open, adaptable, and with strong performance in text generation. Why Grok? Also because it gives us ultra-low latency with deterministic execution. So our methodology based on two phases. Evaluate the system or the case studies. We use two case studies. The first one is an e-commerce application, a mobile clothing sales for mobile clothing sales. The second one is an academic system, EJAB, for the metrics or evaluation. So we used both quantitative and qualitative metrics. The quantitative for to measure the autonomy, semantic accuracy, and traceability. For the qualitative, user trust and usability. So here I specify the product vision for the two applications. The first is a mobile clothing sales app, and the second is the academic process management platform with a current state, desired state, and reviews. So for the first one, reviews are an UX designer and product owner. For the second, the reviews are two research director and two academic coordinator. So the results for the quantitative results for the first application, we have an autonomy and high semantic accuracy, an important success, Jira important success. So we can see that the system performs strongly in structured commercial domains. So for the second one, the academic application, we have the similar autonomy, and we have some inconsistency in following the main steps and some inconsistencies in responses. So for the quantitative results, we have natural interviews and relevant to the context, structured user insights, and acceptance criteria. We can say that are clear enough to develop an application, and the interaction between agents and reviewers was described as assistant-like rather than intrusive. So we evaluate also the human AI collaboration. So as you can see that we have a higher for We have satisfaction for both scenarios. We have a positively rated by practitioners. We have a comparable efficiency gain in both domain for time saved. We have user trust in output for the two domains, and usefulness also. For the quantitative results for the first application, as an input, we have a well-structured backlog. For the second, we have a realistic backlog, but with some short comments. So we can say that AI is perceived as an assistant and not a replacement. So we should have human expertise with our system for validation. So we can see that the framework demonstrates that it is strong automation. He has strong automation capabilities, a good generalization, and preservation of user-centered design. So for the limitations, we have some limitations about prompt sensitivity, generic acceptance criteria, and this also justify the need of human validation. So as a conclusion, we can say that AI can automate backlog generation, and the human AI collaboration improve reliability, and the multi-agent system are effective for Agile. So our future work is to automate all the other steps of Agile processes, sprint planning, backlog refinement, and sprint review, with integrating UX design practices to the system, and also work on domain adaptation. So as you see that we don't have the same results in two domains, commerce domains and education domains, and that's it. So this is our future work for having a great system that integrates UX design and Agile process. And thank you for your attention.
Thank you, Ms. Wafa, for your presentation. So we'll move now to our second speaker, Ms. Hind.
Good morning, everyone. I'm Mrs. Sobbahi Hind. I'm a PhD candidate at LCS Mohammed V University. Today I will present my work, which is entitled Deep Features and Handcrafted Features Descriptors for Iris Recognition. It's a comparative study. So the main objective of this study is to evaluate 12 distinct iris recognition pipelines. We focus on segmentation-free architectures to reduce complexity, computational complexity. We also study the discriminative power of deep features using VG16 and handcrafted features using LBP. The main biometric traits used in this study is the human iris. As we know, the human iris is a very reliable biometric trait. It has unique textures and remains stable over lifetime. This makes it very suitable for identification systems. The main contribution. Sorry. Our main contributions are the following. First, we propose a fully segmentation-free pipeline. Second, we combine deep features with handcrafted descriptors. We also evaluate 12 different variants. Finally, we analyze the system in both identification and verification performance. Traditional iris segmentation systems rely on segmentation. However, segmentation is a complex and error-prone, so we propose a segmentation-free approach. This is the overall workflow of our segmentation-free recognition pipeline. So we first apply a pre-processing phase using the contrast enhancements with the CLAE and DWT for noise reduction. After that, we perform feature extraction using VGG16 for extracting deep features vector, and we use handcrafted features using LBP to extract local texture information. Next, these features are combined through feature using concatenation. Next, we use the SVM and KNN for classification. Finally, we evaluate the system in both identification mode and verification mode. I will now explain each step in more detail. This is the first step, it's the pre-processing step. So we apply a hybrid pre-processing step. We use CLAE for enhancing contrast. We use DWT for noise reduction, and this pre-processing improves image quality while preserving useful information in a segmentation-free pipeline. Now, in this step, we extract features. We use VGG16, a deep learning model, to capture global structures. And we use LBP, it's a handcrafted method, to extract local patterns. These two features are complementary as they provide both global and local information. And this combination improves the representation of iris patterns. After that, we make the fusion. We combine both features, deep vector with the handcrafted vector. This creates a high-dimensional feature representation. We see the final hybrid vector is a high-dimensional vector. As a result, these two types of feature provide both global and local information. After that, we have the phase of classification. In this step, we use two classifiers. We use SVM and KNN as the baseline. For optimization, we use the randomized search CV, and we make five-fold cross-validation to prevent overfitting. So for the experimental design and evaluation, we have evaluated our system in two modes, in identification mode, using the accuracy and the confusion matrix. For the verification mode, we use the error, equal error rates and the log curves, and the cross dataset analysis. The results of our baseline, we first evaluate in raw images. The best results is obtained with the VGG60 with the classifier SVM. The accuracy reached 97.77%, but this configuration is sensitive to noise. For that, we have applied the pre-processing step. After applying CLI and DWT, the result reached 98%, 44%. This improvement demonstrates that the effectiveness of the hybrid processing strategy. And it also confirmed that enhancing image quality helps extract more discriminative features. Here, this figure presents a comparison of all 12 variance analysis, as we observe that SVM outperforms KNN across all configurations. We see also that LBP alone is not enough, is not sufficient. And this confirmed effectiveness of combining deep and handcrafted features. In this slide, we show the confusion matrices of our models. On the left, we observe the best configuration. The strong diagonal indicates that the most samples are correctly classified. This means that the model is has a high reliability. And on the right, we see a weaker model. There are more scattered points, which represent misclassifications. For generalization and verification performance, this slide, we observe that performance is better in the Casia synthetic database with an ER of 16.5%. But in contrast, in the real world, in IITD, data is more challenging because it's leading a higher ER of 23.6%. This confirms that, despite this, the system remains strong in maintaining strong discriminative capability with an AUC which reached 0.90%. This confirms the effectiveness of our segmentation-free pipelines. In this slide, we compare identification and verification performance. In identification performance, the system achieves high accuracy, but in verification mode, the task is more challenging. This is due to noise and the special variation in real-world data. Overall, we conclude that segmentation-free pipelines are highly suitable for fast identification, but less optimal for strict verification tasks. For future work, we plan to explore vision transformers. These models can capture global patterns better than CNNs. We will test VIT architectures and study their performance. And the main goal is to balance accuracy and computational cost. To conclude, our result shows that combining VGG16 with SVM provides best identification performance while keeping the model simple without pre-processing step. Without segmentation step. We also observed that hybrid preprocessing using CLAE and DYT improves the quality of iris patterns. Overall, segmentation-free designs are effective for fast, efficient identification, but it's still more challenging for verification tasks. That's all. Thank you.
Thank you, Madam, for the presentation. So we move on to our third speaker, Mr. Rahul.
Hi everyone, I'm Rahul. Hi everyone, I'm Rahul. I'll be presenting my work on emergent behaviors of predicting glaucoma, which is a irreversible eye blindness. So to put it, I mean the title is too big, I know that, but to put it better, it's just using machine learning techniques to, in a smart way, predict and see how the retinal disc and cup segmentation is in order to see how the irreversible blindness is. Yeah, so I'll be getting into the motivation behind this work and explaining a concept of classifiability limit, which I'll come into explaining in the upcoming slides. And the data set that I used was GS, which is basically has 50 training sets and 51 test images of retinal eye images. And yeah, I'll be moving on. So the motivation behind this study was that because glaucoma is one of the most leading irreversible eye blindness that actually takes place. And the worst thing is that this cannot be seen. Yeah. So the worst thing is that glaucoma is something that cannot be predicted in a way which other diseases are, because the symptoms come at a very last stage, and once it comes, it's something that cannot be treated that easily. So trying to see into glaucomas, basically this is how the image looks once the picture of the retinal image is taken. So it's called the fundus image. So the outer region here is actually the disc, and then the one inside is the cup. So basically what happens, to be short in glaucoma, is that this is the region where the boundary of the nerve, the connection between the nerve and then the eye is. So the cup, the inner segment of this, it gets larger and larger. So once the inner segment gets larger and larger, that leads to blindness. And this is how it goes on. So there is, it's measured using the CDR, which is the cup disc ratio. So it uses the, it primarily uses the cup's diameter, and then it's divided by the vertical diameter of the disc, and through which we can see the ratio of how the cup is actually expanding further and further, which leads to blindness eventually. Yeah. So getting into the concept of classifiability limit, this was actually one of the paper that one of the co-author of this work actually presented in his previous work, Professor Carlos, who's here. So this was a theoretical framework of seeing how the limit of two classes actually goes beyond a certain point. So to put it simple, in every sort of deep learning models, for instance, this work uses the unit model. So once the retinal photograph is actually taken, the doctors or the experts actually try to segment the boundaries based on manually looking at the image, trying to see where the disk and the cup boundaries lie. And then they draw the boundary just by looking at the image. And that differs from person to person because the image that's taken usually fades off after a certain point with respect to the disk and cup segmentation. So in that case, let's say there are various experts who look at an image, they draw different segment lines. So it wouldn't align with another person who actually drew the segment boundary. So that is one of the major issues which we actually encounter here. So in one of the papers which actually introduced the concept of classifiability limit was the art of misclassification. And in that, they actually tried using mathematically prove it through entropy analysis, where they try seeing how the class distribution is genuinely overlaps the data. So in that case, this is simply trying to see how the two feature classes actually, after a certain point, cannot be classified, and it goes beyond a certain limit, which is not an issue with the model or the data. But then, as I mentioned earlier, when 2 different or 3 different experts come into conclusion of looking at an image, it differs from person to person. So that's not an issue with data or, let's say, with the model. It's the issue of where something which is irreversible in terms of looking into the model, and that's what classifiability limit in general means. It's like a hard ceiling which cannot be achieved after a point is what classifiability limit actually means. Yeah, so the data set, as I explained earlier, had 101 images. So in total it was 50 images for training and 51 for the test. And 4 expert annotators were there. So basically what they do is the concept of soft map comes in here, where they look at the image and then they draw the boundaries based on the pixels of the image. And in that case, it's given to 4 different experts and it's ranked based on what each of them actually try to draw the boundary at. So let's say if all 4 agree upon the same boundary, they get a score, and if they don't, the score goes 0. So there's a binary masking that actually, which I did, so which is like the hard masking of threshold. So it is around 0.75 if at least 3 of the 4 experts come into a conclusion that that's the genuine boundary that they classify. So I used a unit network here. So this was a well-established encoder-decoder structure. So where we are trying to see the architecture specifically with regard to how the medical images are, medical image segmentation comes into picture. So the encoder actually compresses of the image where there is a down layering by layer, and then the learning process actually takes place over there. And the features here actually matter, and when we try to see the decoder, it basically expands and it backs it up. So in that case, it is basically reconstructing exactly where each of these structure is supposed to be. So basically, it looks into the shortcut connections between the encoder and decoder and preserves the boundary of those particular details. And we added 2 output heads over here. So one was the standard unit. So that basically predicts the optic disk mask. And then the other one is the optic cup mask. So both produced simultaneously. It's basically a shared network there. So in that case, we trained it completely based on from the scratch with just the 50 training images, and we actually purposefully kept the other 51 test images were running into the model to see whether if the soft map and then the model actually learns better. And in that case, there was no weights that were actually borrowed from any other data set or any other external data set, because papers that currently use such ideas actually train their model based on various other data sets before getting into what they actually try doing. So the model actually is well trained in that case with other data sets to easily understand, but in this case, purposefully I've restricted it to this particular data set to see how the process of the unit model actually takes place. So version 1 was basically looking at the baseline, and that was basically converting the soft map into a hard binary mask by giving it a threshold. So at a 0.75 that I previously mentioned, so the training happens with a loss, and then what happens is every single pixel is actually treated in a way in which it gives an equal weight regardless of whether all 4 doctors actually agreed to that particular segmentation or not. And then the second version is that, which is basically the version that we proposed, which basically looks into the soft map values and then it computes pixel by pixel based on the weight. So for example, if majority of the 4 experts are given the boundary segmentation at that particular pixel, it gives more weightage in the learning process towards that. So the outcome is better in that way. And here it's the proposed way was giving it the weight. So weight would be 0.5 regardless of whether the experts actually accepted it to or not. Then the soft map weight. So basically we are trying to see giving 1 as a weight if it is accepted by the experts, and then we are mapping it with the soft map scores that the experts have given. So the weight while the model is trained is given accordingly. So the results here, again, looking at the results, is basically the disk size, which is measured between the overlap of our predicted disks of the retinal fundus image and the region where the experts have drawn the risk boundary. So that's basically what the baseline disk size tries to say. So it's basically like a scoring in terms of percentage that we are trying to see, where you can think it of like a percentage match, where if it is 1, it is perfectly aligned with the expert opinion with whatever the model predicted, and with 0 if there is no any overlap overall. And our baseline actually 0.894, which is actually about a 89% match with what the experts actually identified the boundary of the retinal image. And then the consensus weighted models actually improved it. So when the baseline was 89%, and when the model actually was given equal weights based on the soft mapping, the model was able to predict better in terms of the results. We got 0.9085, which is again a 7.5% gain compared to the baseline. And the disk boundary was, the cup size measure was the same thing for the cup, which the disk size has done, but it's for the cup. So because the boundary is more ambiguous, you could exactly see the classifiability limit that comes into picture over here, because the baseline was around 0.692 and we improved it to 0.74. So that is basically a 7.5% gain in terms of that. And then the CDR ratio, which is the cup disk ratio error, was again an average difference between the ratio cups, and then the expert measured CDR was somewhat around 0.185, and it was increased to 0.14, which was a 21% improvement in terms of what the model actually was able to learn. And all 5 of these metrics were statistically significant, so there was no any error for a chance that actually happened. So, and obviously the limitations is we just trained the whole model on just 50 images, so that's a very small data set, which is arguably true, and it's based on a limited laboratory set the data was actually collected. So again, it is going to talk different with regard to other real life images, and also the photography quality of what the retinal images is different from each and every time and different data set has. So the future work is basically to bring in a soft label supervision where we try to predict it based on the probabilities of the soft map, and also bring in cross-validation and external validation into the study. So, in conclusion, I would like to say that the classifiability limit tells us actually where the classification distributions are generally overlapping with the data. So no model can actually exceed the hard ceiling that we saw previously with the results, where in our case the overlap was the cup unbounded, which was genuinely ambiguous with regard to the results that we got. And instead of ignoring the overlap, we used the binary masking with regard to the soft map. And in that case, it was better in terms of the learning process. And the pixels that the doctors actually disregarded, the experts actually disregarded, was still taken into account by giving 0.5 as a weight, not ignoring it completely out of the model. So basically, the classifiability limit tells the ceiling where we can't actually achieve that variability in terms of what the experts actually say and then the models predict. And that shows how the encode actually overlaps the structure in terms of the what training actually can do with regard to any model that we use.
Thank you, Rahul, for the presentation. So we move now to our last speaker, Mrs. Wafae Ayachi.
Hello everyone, thank you for being here today. My name is Ayachi Wafae. I am currently a first year PhD student at the Mkhimri School of Engineers. I am pleased to present our work entitled OS2-based indoor mapping dataset acquired in an academic building using Tutubot 4. This work was carried out under the supervision of Professor Mohamed Abu Zaid within the Lastemi laboratory. To begin this presentation is organized as follows. First, I will introduce the motivation and the objective of this work. Then I will present the proposed system and the dataset construction process. After that, I will summarize the main experimental results and practical relevance. Finally, I will conclude and discuss future perspectives. Let's start with the motivation and the problem statement. Autonomous indoor robots must are expected to perceive their surroundings, estimate their position, and navigate safely in complex environments. Achieving these capabilities depends strongly on reliable localization and mapping algorithms, practically SLAM. However, the fair evaluation of such a method requires realistic benchmark data sets acquired under representative operating conditions and realistic environments. Although several public datasets they don't rely on modern platforms or software ecosystem. As a result, datasets aligned with modern RAS2 robotic ecosystems remain relatively limited, and this gap motivated the development of our proposed dataset. To address this need, the main goal of this work was to develop a realistic multi-sensor indoor dataset fully compatible with ROS2 for SLAM and autonomous navigation evaluation. Our contribution is mainly a real academic environment with multiple buttons and floors. It includes multi-sensor data such as LiDAR, odometry, MEO, AGBD camera. And it is a ROS2 native workflow used in SLAM Toolbox and NAVTOol. The data is structured to be reusable and for benchmarking. To better understand the proposed work, let us briefly look at the overall system architecture. The dataset was collected using Tutubot 4, a mobile robot equipped with multiple sensors. The collected sensor data is managed to a ROS2 framework, ensuring communication between different system components. SLAM Toolbox was used to generate occupancy grid maps later used for navigation and localization with the nav2 framework. In this way, the system provides a complete pipeline for data acquisition to navigation validation. Based on this architecture, the next step was to perform mapping and navigation tasks. First, regarding the mapping, LiDAR and odometer data is used to generate the occupancy grid map. It is a real 2D SLAM performed using SLAM Toolbox. The maps capture indoor layouts such as corridors and rooms. The generated maps are exported for later use. And for the navigation, the generated map reused within the nav2 framework. Robot localization performed using EMCL, collision-free path planning towards target goals. Velocity command sent to the command wave command. To generate the proposed dataset, the next stage focuses on data acquisition in real indoor conditions. The recordings were carried out inside the higher school of technology of Sali. Several buildings and floors were explored in order to capture diverse indoor environments. These environments include complex geometrical forms. During the acquisition sessions, the robot was mainly driven at a controlled speed of approximately 0.2 meters per second. The following table summarizes the 6 acquisition sequences and their main characteristics, including recording duration and collected data volume. The resulting dataset include several. Once the data was collected, the next step was to organize the dataset in a clear and reusable structure. The complete dataset was arranged by building and by floor in order to simplify access to each acquisition session. For every sequence, ROS2 bag files were provided for a play of the recorded experiments. The generated occupancy group maps were also exported in PGM and YAML formats. In addition, CSV files were included for sensor data analysis outside the ROS2 environment. This structure organization improves reproducibility and makes the dataset easier to use for future research and benchmark. As for the results, the resulting dataset includes several useful outputs. First, we got 6 occupancy grid maps were successfully produced using SLAM Toolbox from synchronized LiDAR and odometer data. These maps clearly represent the real structure of different explored flow and open areas. They were also exported for later reuse. In addition, one video recording was provided for each acquisition session. We also have the ROS2 bag files stored in a .db3 format. All acquisition sequences stored by recording. It represented the original timestamps of LiDAR, odometry, and RGB streams. It enables synchronized offline replay of experiments. It is suitable for benchmarking SLAM and navigation algorithm. And we have also exported the CSV sensor data. It represented the sensor stream exported format from original recordings. It includes timestamps measurement for external process, and it facilitates usage outside the ROS2 ecosystem. The following table highlights the practical value of the proposed dataset. The acquisition sequence have different durations, which creates more diverse test scenarios. The acquisition sequences also show different topic rates, reflecting different sensing conditions and data densities. In addition, the acquisition sequences have different data value from smaller to larger recording. This is useful for realistic benchmarking tests. Finally, the multimodal synchronized stream supports reproducible SLAM and navigation evaluation. For the conclusion, this work represents a realistic ROS2-based indoor dataset acquired using TotalBot4 in an academic environment. It collected synchronized LiDAR, odometry, and RGB recording across multiple buildings and floors. We generated occupancy group maps and reusable multi-format outputs, ROS2-backed CSV files video. It demonstrates suitability for SLAM, localization, and autonomous navigation evaluation. It also provides a reproducible benchmark research for future robot research. Thank you for your attention.